Look up at the night sky. The brilliant stars, the swirling galaxies, that massive cosmic tapestry that has captivated humanity for literally millennia. But what if I told you that everything you are looking at right now, everything we can see, touch, and measure, is just a tiny cosmic bit player? Welcome to The Explainer. Today, we are venturing out into the cosmos to demystify the 95% of our universe that is completely invisible to us.
So, here's our game plan. First, the invisible universe. Second, discovering the unseen. Third, building the cosmic web. Fourth, the leading candidates. And finally, fifth, dark matter versus dark energy. We are going to trace the epic history of the universe from the Big Bang to its ultimate fate by tracking the unseen forces that shaped absolutely everything we know.
Part 1. The Invisible Universe.
All right, let's start with a reality check that is honestly kind of mind-bending. Everything we are familiar with, planets, stars, gas clouds, and even your own body, it makes up a mere 5% of the mass-energy content of the universe. Just 5%. The rest, it is completely hidden from our eyes and our standard telescopes. About 27% is composed of a mysterious substance we call dark matter, and a staggering 68% is made of an even more perplexing force known as dark energy. Okay, let's dive into this dark matter stuff. Actually, the term dark matter is a bit misleading. It would probably be better described as transparent matter. Because if you were to shine a laser beam right at it, the beam would pass seamlessly right through. It doesn't absorb, reflect, or emit any light across the entire electromagnetic spectrum. But we know for sure it's a form of matter because it has mass, it takes up space, and most importantly, it exerts a gravitational pull. It basically acts as the invisible glue holding entire galaxy clusters together. Section 2. Discovering the unseen. So if we literally can't see this transparent matter, and it doesn't interact with light at all, how on earth did rogue astronomers figure out it was even there in the first place? I mean, it's like arriving at a crime scene where the perpetrator is completely invisible. Well, this detective story actually spans nearly a century. Back in 1884, Lord Kelvin noted some early hints of unseen mass. But the first real breakthrough, that happened in the 1930s. A Swiss astronomer named Fritz Zwicky noticed that galaxies in the Coma cluster were moving way too fast. Like, so fast, they should have torn the whole cluster apart. So he concluded there had to be some unseen mass, which he dubbed Dunkel materia, providing the extra gravity to hold it all together. His radical theory was actually ignored for decades, until astronomer Vera Rubin came onto the scene in the 1970s. Now, Vera Rubin was studying the rotation of spiral galaxies, like Andromeda. Based on standard physics, she fully expected the stars at the outer edge of the galaxy to orbit much slower than the stars packed near the dense center. Just like the outer planets in our solar system orbit the sun slower than the inner ones. But she observed something absolutely startling. The stars at the very outer edge were moving just as fast as the inner stars. The entire galaxy was spinning almost like a solid wheel. Mathematically, the only explanation was that a massive, invisible halo of matter was surrounding the galaxy, providing the gravitational muscle to keep those fast-moving outer stars from just flying off into intergalactic space. Thanks to her, the scientific community finally had to accept that this unseen stuff was very, very real. Section 3. Building the cosmic web. Let's rewind all the way back to the birth of the universe and see how dark matter actually acted as the master builder of the cosmos. So structure formed from the absolute chaos of the Big Bang about 13.8 billion years ago. In the very first fractions of a second, the universe expanded exponentially, freezing these tiny ripples of differing density right into the cosmos. And because dark matter doesn't interact with radiation, it was able to clump together really early on, forming massive filaments. Think of it like a giant invisible spider web covered in morning dew. Its intense gravity pulled in all those primordial gases, which then pulled at the dense intersections and eventually ignited the very first stars and galaxies. Now, this part is absolutely wild to think about. The early universe was in an incredibly cramped, dense, and hot place. Dark matter particles would have been crammed so tightly together that violent collisions were inevitable. When these massive, invisible particles smashed into each other, they would have annihilated, releasing huge bursts of energy and actually spawning new subatomic particles of ordinary matter. So it is incredibly plausible that the electrons currently flowing through your nervous system right now were forged in the fiery collision of two dark matter particles shortly after the Big Bang. Plus, some scientists even theorize that the first stars, these massive puffy objects known as dark stars, were literally powered not by standard nuclear fusion, but by the heat of dark matter annihilating right inside their cores. Which brings us to Section 4, the leading candidates. Scientists have this massive cosmic suspect list. They know the stuff has mass, they know it's invisible, and they know it moves relatively slowly. But its exact identity? Still at large.
The top suspects currently fall into a few distinct camps. First up, we've got WIMPs, weakly interacting massive particles. These are heavy, slow-moving, hypothetical particles forged in the Big Bang that barely interact with normal matter, which means literally millions of them could be passing right through your hand at this very second. Next, we have axions. These are incredibly lightweight, low-energy subatomic particles that were originally theorized just to solve a complex mathematical symmetry issue in particle physics. But if they exist, they could totally account for dark matter. And finally, primordial black holes. These are ancient, ultra-dense objects that collapsed not from dying stars, but from dense pockets of matter just fractions of a second after the Big Bang.
Now, primordial black holes are a highly appealing theory, right? Because it means dark matter wouldn't require us to find any brand new, undiscovered subatomic particles. It would just be black holes, ranging anywhere from the size of an atom to thousands of times the mass of our sun. But there is a catch. Recent data from the LIGO Observatory, which detects gravitational waves from colliding black holes, suggests a pretty big problem. See, if the universe was absolutely flooded with enough primordial black holes to account for all of the dark matter, LIGO should be detecting thousands of collisions. But they see way, way fewer than that. So that discrepancy casts some serious doubt on the idea that primordial black holes can explain the whole dark matter mystery.
Section 5. Dark matter versus dark energy. So we've talked extensively about dark matter. But what about the other mysterious force making up 68% of the universe? There is an epic 13.8 billion-year battle playing out right now across the cosmos. Dark matter and dark energy are locked in this relentless struggle. Dark matter works through gravity. It is the great constructor, constantly trying to pull matter together to build galaxies and clusters. Dark energy, on the other hand, it's the great destroyer. It acts as a sort of anti-gravity, a repulsive force that's inherent to the vacuum of space itself, and it is relentlessly pushing the universe apart. Let's look at how this battle actually unfolded across cosmic history. For the first 9 billion years after the Big Bang, dark matter was totally winning the war. It dominated the universe, pulling gas and dust together to build that magnificent cosmic web of galaxies we see today. But dark matter's success actually set up its own downfall. As it pulled matter into dense filaments, it left behind these massive empty gaps called cosmic voids. And dark energy lurks in those voids. About 5 billion years ago, as those voids grew large enough, the repulsive force of dark energy cumulatively overpowered the attractive pull of dark matter. The expansion of the universe didn't just continue, it began to aggressively accelerate. And because dark energy is a property of space itself, well, as space stretches out, more dark energy is effectively created, which just supercharges the expansion.
So, what does this all mean for our future? Well, in about 100 billion years, this unstoppable, accelerating expansion driven by dark energy is going to stretch the fabric of the cosmos to an extreme limit. It will literally push all galaxies outside of our local cosmic group so far away and so fast that their light will never be able to reach us. They will be pushed completely beyond our cosmic horizon. To put that into perspective, to future astronomers, the universe will appear to consist of just our single, lonely, isolated galaxy surrounded by an endless dark void.
And that leaves us with the ultimate question. We used to think the fate of the cosmos rested on dark matter, but we now know it depends entirely on dark energy. Will this repulsive force just continue to accelerate until it rips apart galaxies, solar systems, and eventually atoms themselves? Or will dark energy one day decay, allowing the universe to collapse back in on itself? The ultimate fate of the universe rests entirely in the dark, leaving us to wonder, what other profound secrets remain hidden in the invisible cosmos?